Hello, thank you so much for tuning to my YouTube channel. Today's video is gonna be a step-by-step tutorial on classifying handwritten digits using neural network. I'm gonna be walking you guys through the steps of the coding of this problem. Let's get started. As I said, this video is a step-by-step tutorial on classifying handwritten digits using neural networks. The problem we're trying to solve here is to classify grayscale images of handwritten digits 28 by 28 pixels in size into their 10 categories, 0 through 9. We'll use the MNIST dataset, a classic in machine learning community, which has been around almost as long as the field itself and has been intensively studied. It's a set of 60,000 training images plus 10,000 test images assembled by the National Institute of Standards and Technology in 1980s. The workflow will be as follows. First, we'll feed the neural network the training data, train images, and train labels. The network will then learn to associate images and labels. Finally, we'll ask the network to produce predictions for test images. And we'll verify whether these predictions match the labels from test labels. Here, our network consists of a sequence of two dense layers, which are densely connected, also called fully connected neural layers. The second layer, which is the last layer, is a 10-way softmax layer, which means it will return an array of 10 probability scores, summing to 1. Each score will be the probability that the current digit image belongs to one of our 10-digit classes. Let's go to Python and code this problem there. Okay, let's get to the coding part of the video. And as you can see, I'm going to be coding, as I said before, in the Colab. And it's very cool. It has everything ready, and I'm just going to be coding in it. Let's get started. First, I say from keras datasets import MNIST, and then I'm gonna be assigning them to train images and train labels. And then again, test images and test labels. Yeah, so and then I'm going to be saying MNIST load data. Awesome. To check that I have done this part right, I'm going to be like train images shape. Let me first get connected to the GPU. Awesome. It is connected now. I'm just going to be checking the train images shape and train and test images shape. Let's say test images shape. Okay, this is the test image shape. Let me also check the train image shape. All good. And I'm gonna be just comment this one out. I don't want to be running it again. Let's open up another coding right here, and let's start building the network. We say from keras import models, and then from keras import layers. Sorry, I have to write this here. And then network would be models sequential. And yeah, that would be it. You gotta be cautious because sequential should be S should be capital. Now we're gonna add the layers with network, add layers, dense layers, and I'm gonna have 512 neurons. The activation is gonna be ReLU, and input shape is gonna be 28 by 28. Now adding the last layer, network, add layers, dense, this time 10 activation, this time 10 neurons with activation function softmax. And yeah, that's it. And let's compile the network compile with optimizer RMS prop, and then the loss function would be categorical cross entropy and metrics accuracy. So now, before training, we'll have to pre-process the data by reshaping it into the shape that the network accepts and also scaling it so that all values are in the range of 0 and 1. So as we know, our training images are stored in an array of shapes 60,000 and 28 by 28, and also their values are in the range of 0 and 255. So we're gonna have to change that. So we're gonna say train images reshape 60,000 28 by 28, and also train images as type float 32 over 255. So this is where we are normalizing the data so that they would be between 0 and 1. And this is where we are reshaping them. We're gonna have to do the same thing but for the test images. So let's just copy it and then paste, but then we write test. And also this is 10,000. Same thing here. Test. At this point, we also need to categorically encode the labels. We use toCategorical to transform our training data, the labels, before we pass it to our model. We can't simply train a classification model without this. So we write from keras utils import toCategorical, and then train labels toCategorical, train labels, and the same thing for the test labels, to categorical, and then test labels. Now we could go ahead and fit the model. Network.fit train images, train labels. We're gonna put epochs to 5. And then the batch size, we're gonna set that to 128. You could use any other number, but I just used epochs 5 and batch size 128. And let's evaluate the model. Test loss, and then test accuracy would be network evaluate, and then test images and test labels. This is the moment of truth where you apply your network to your test data. And let's print out test accuracy, which would be equal to test ACC. Yeah, let's run it and see if it works. Hopefully it's gonna work. Let's just run this one. As you can see, it's going through the epochs. So as you can see, this is the training accuracy and this is the test accuracy. If the training accuracy is a lot higher than the test accuracy, that means your network has become overfit to your train data. But as you can see here, the accuracies in both cases is the same, which means our network has not become overfit to our training data, which is a good sign. And one reason might be the lower number of epochs. The higher number of epochs you use, the chance of your network becoming overfit to your trained data is going to be higher. But here we're only using 5 epochs, which would not give our network a chance to become overfit to our trained data, as you can see in the accuracy of the train and test data. And that's about it. Thank you so much for watching this video. I hope you liked it and you were able to get something out of it. If you liked it, I would appreciate it if you could subscribe to my channel and also share the video with your friends. Thank you.